So hello again, and we're now going to look at the software. However, before we do that, we're just going to look at a few things that, a few corrections in the last two videos. Not really so much corrections, but comments I need to make. In the first one, in the very first video, I mentioned about inclinometer, and the only reason I mentioned inclinometer rather than magnetometer was because I'm working on a project for ELEC2540 for next year, and inclinometer was in my mind. That's an angular position thing and not a magnetometer thing, which is actually cardinal compass positions. So I apologize for that. When you're looking at the first video, which is a retrospective type of thing, I was meant to be referring to a magnetometer, not an inclinometer. And in the second video, which was the one about the schematic, which I have in front of me here, I just want to point out that the reason for creating plus or minus 5 volts is that the op amps that are used in these circuits, so let's just go to our output channel, which generates our plus or minus 1.25 volts, which we talked about. In order to generate that plus or minus 1.25 volts, we need op amps that are powered with a signal that is actually generally higher than that, and that's one of the reasons also why we generate plus 5 and minus 5. The LM358 is a very good amplifier, very good general purpose amplifier, but it's not a rail-to-rail amplifier. You may or may not have heard of rail-to-rail amplifiers, but these amplifiers allow you to go to whatever the supply rails are. So if your op amp is powered from 0 to 5 volts, then the output is actually quite capable of actually going to 0 and 5 volts, which is pretty amazing, really. However, many amplifiers are not like that, and if you try and drive them anywhere close to their power supplies, they just saturate and fail. So they just don't produce a signal up to the value of the power rails. Now, the LM358 is a very good general purpose amplifier, and one of the reasons why we've got a reference of 2.5 volts and generating voltages of plus or minus 1.25 volts is so that the op amps can be powered from plus 5 and minus 5, which is well within the limits of the amplifier to generate those voltages accurately. So I just wanted to clarify that, so a little bit more information and something that could actually be quite useful for your futures. Yeah, consider this when you're dealing with amplifiers in analog circuits. You might find it quite useful. So anyway, what we're going to look at is the software associated with the compass control unit. So let me just move to here, and what I've done here is I've opened up the main .c file of the software. This software will be very familiar to MEC2200 students who have been using the same microcontroller for their MEC2200 project, and so they will understand a lot of what's on here. But for those of you who haven't done MEC2200, then this will be a little bit bit weird, and I don't get any of this. I totally get it, totally understand it. If you want to know more, then please ask me, and I will very happy to explain some of this. But learning to program microchip devices is actually quite advantageous to your careers, and hence the reason I'm teaching MEC2200 students all about this, and they've been embracing this much to my delight, which is fantastic. So I'm not going to go into the fine detail of a lot of this, but these are just declarations. But what you have to understand is that when you first power up the compass control unit, you end up with a HMI screen, and I've got an image here of the screen. I just hope you can see that in this window here. I don't know whether I can zoom in on that. Let's just zoom in a little bit. Oh, that's very good. Right, that's the HMI. Right, so this is what you'll see when you first power up the system, and you'll see a system status message, and all this information is coming from the microcontroller. So there's no high-end software on this. They're sitting in the Windows environment. This is all generated using a terminal emulation software package, which is MTTTY. And this is what you'll see when it first powers up. And all of this is coming from the software that's been written for the compass control unit. And so you'll see that we've got a status message about the oscillator not being calibrated, which is fine. Positive and negative voltages, display values. This is actually a live system I was running, and so this is real information that came from the system I had on my dining room table. And you'll see that we've got the positive and negative voltages represented here, which we discussed when we looked at the schematic. And we've got a present compass position. This is an instantaneous value of where the compass actually is when it actually does the initialization and takes in data to find out, make sure the I2C is working, and to pull in a value from the compass. And it's saying it's actually 42.7 degrees. So that would have come in from the compass as 427 and has been re-represented as 42.7 degrees. And also you'll see on here the calibration. So we need to calibrate the oscillator. And remember, we discussed in the schematic that we are using an RC oscillator internal to the microcontroller. So what I do is I actually generate on the trigger output a 500 Hertz signal. And what I'm doing is actually going to use that, or what you would do in the real experiment is you would actually connect that output, the trigger output, to your oscilloscope. And you would actually then be monitoring the square wave that comes out of this output, which should be at 500 Hertz. And what you'll find is that if you, when we actually do this experiment, and you'll see this for real, when I go through the other videos that are in this lab, then as we adjust the characters that control the tuning of the oscillator, I can actually tune it in to actually generate a frequency of 500 Hertz. But we will go through that, make a bit more sense when we actually do it for real. And also, once we've got the oscillator calibrated, then we can adjust the null point of the servo. Now, something that wasn't fully discussed in the previous video was that we mentioned the accuracy of the oscillator that drives the embedded micro, but if it isn't correct and it isn't precise, then what happens is the continuous servos, by their nature, will generally start to rotate very, very slowly, but a little bit at a time, because the null point hasn't been set. And so what we're going to do is we're going to be able to adjust the null point of the servo. Now, this is the PWM pulse width, which is nominally 1.5 milliseconds. Well, in order to stop the compass from moving at all, when it's not being told, when it's been given a signal of effectively 1.5 milliseconds, what we're trying to do is get the servo to stay still. Now, I did mention that there's a little pot that you can tweak on the potentiometer. It's a little potentiometer on the actual continuous servo itself, but once that's locked in the case and you can't adjust it anymore, it was roughly adjusted when it was built, but beyond that, it's just generally will slowly move. Once you power it all up, the pointer will very, very slowly move in one particular direction, and we can null that out. So that it means that at a PWM period of 1.5 milliseconds, we can adjust that slightly so that we can actually get it so this servo stays still and so it doesn't move. And when we go through that, it's part of the experiment, and we'll see that for real through the videos and me playing with it, and then you'll understand what this actually means and what it's actually trying to do. And then we have another option here, which allows us to test the DACs. Now, with any hardware, you want to make sure it's all working correctly. So this allows you to test the DACs, and we're going to generate a sawtooth waveform. What we're going to do is generate a waveform that looks a bit like this. So you'll see this waveform here. So what I'm doing here is actually ramping up the DAC outputs from 0 through to their full range output of 2.5 volts. And you'll notice from this scope image, I'm hoping you can actually see it quite clearly. Let's see if I can zoom in a bit, view and zoom in. Yes, let's look at it a little more clearly. This is actually quite good, because what you'll also see is it steps as it's going through this change. So there are basically 1023 steps as it's doing this waveform. And you'll also notice there's the 0 point of the oscilloscope here. And what you're seeing is a rise to, we're on 1 volt per division, so there's a peak of plus 1.25 volts and there's the low of minus 1.25 volts. And you'll also notice that there are steps in here. Now, why do you think there's actually this slight square wave relationship? You have to just consider that the software isn't instantaneous. So it takes a certain amount of time to change the actual value in the DACs and for it to actually execute that software. So these little linear steps that are sitting in here, I don't know how clearly you can see this, is an example of the time it takes for the software to execute the command to change the DAC value from one value to the next value. So actually incrementing and decrementing by 1. So it's here it's actually, remember this is all inverted because the op amps at the output actually invert the output signal. So for a positive rise from the DAC you get a negative fall in the output. So this is where the DAC is actually physically being, let's see, this is being decreased, so this is going towards 0, so this would be the 0 output from the DAC, and this would be a plus 2.5 volts on the DAC, or set to 1023 in the DAC registers. But all of these little steps are the time it takes. And if I can zoom in a little bit more, I don't know whether we can see this in fine detail, you might be able to just see that flattening of this waveform. And this, if we were to expand this from a timescale perspective on the scope, then we could actually see how long it takes the software to execute the commands which we're about to see when we look at the actual software. So these lines are all to do with the timing of the software. So let's just zoom out of that again. Right, so let's go back to our HMI again. So that's test the DACs, and that's the waveform we would expect to see coming out of it. And also the HMI allows us to set the compass to approximate north and also set it to approximate south. Now, why would you do that? Well, one, there's a test feature here so that we can actually double check that everything is working as it should be. However, there's a really important one here of setting the compass south. If you're analyzing a control system, you actually want to see how it really performs when you've got the worst case scenario. We are aiming to get this compass to only point north, and that's its main task as a control system, because that's a bit like our set point, like I discussed, like having an oven that's set to 200 degrees centigrade, and the oven wants to try and get to 200 degrees centigrade, and so it switches the power on to heat the heaters to actually generate the heat in the oven to get to that point. And once it gets to that point, it switches the oven off, and then it keeps on cycling backwards and forwards, trying to maintain that temperature. Well, this is, so really from a control system perspective, we're looking at the worst case scenario, which is what is the worst position this compass can be at, and it trying to aim to get back to its final destination, which is north. Well, that's south, because that's the furthest point away. So by moving the compass to a south position, it allows us, when we run our control algorithms, to look at the algorithm's performance from a worst case scenario. And that's the reason these commands are in here. And you'll see these in the sub menus associated with these, which are actually running our control algorithms. So that's one part, but then we've got 6 and 7 here, which allow us to rotate the compass in a clockwise direction or rotate it in an anti-clockwise direction. So what's the purpose of this? Well, this allows us to characterize our servo, because at the moment we have no idea whether our servo is a linear response. So as I gradually change the PWM pulse width, does it actually change linear, or does it saturate, or what happens? We don't really know yet. And so by allowing us to control the compass speed of rotation in a clockwise or anti-clockwise direction, it allows us to assess the performance and transfer characteristics of the actual servo. And this is really important to understand when it comes to control systems, because it allows us to assess the algorithms that are used and actually what is really expected from our response curves in terms of how well can the system respond to changes, and also from extreme changes such as moving it totally to south. And these latter ones, 8, 9 and 10, are the actual algorithms themselves. And we're not going to look at the software for these yet, because I don't want to confuse you and it's not appropriate at this point in time. But what I do want to do is just look at this in general so that you get an idea of how this system is actually working. So we'll just minimize those. And now we're going to look at the software. So here you'll see a lot of status messages. These are messages in the software. So these are strings that have been loaded in the software. You'll probably be very familiar with this if you've been doing embedded software design. And so you'll see all the messages that we just saw on the screen earlier on are actually in here as option messages, and there they all are as code. So we also have error string messages. This tells from a HMI perspective if you've entered a number that's out of range. This is really good practice when we're dealing with HMI, especially with student work where you could make mistakes, and it's basically informing you of a mistake you might made, whether the number's too large or the number's too small or it's too long, etc. So these are error messages in the software that just help us to get over this problem. And then these are associated directly with the actual functions in terms of the algorithms. And here's our main status screen, which tells us the oscillator calibration status, the voltage, voltage levels, etc. And there's some additional ones here which are tied into the software in different sort of ways. But this is where all the messages are kept. So these are global variables that I'm using. This is the initialization of all the port bits, which I'm sure MEC 2200 will be very familiar with. And here we have the initialization of bits and pieces. So we've got the initialization of the comms, which allows us to talk at 9,600 bits per second to our MTTY software. We're setting up some timers, and once again, remember the timers, the quality and the accuracy of the timers is dependent on the precision of the oscillator that's actually driving the software in the first place. We're setting up the DACs. Now let's have a little look at the DACs, because I said to you that one of the things that we do is ensure that you've got 0 volts coming out of the test points during initialization. Well, if we go into the DAC software, it's going to do that, yes. And let's have a look here. This is the initialization function for DACs, and we'll see an instruction here. Let me just zoom in on that if I can. There we go, might be a little bit easier to see. So you'll see that DAC1 is given the value 512. And as we discussed in the schematic, the value of 512 will produce 0 on the test point output. And we've got 4 of these. So there's our DAC1 ref, there's our DAC2 ref. Now, these are registers inside the micro. This changes at our test point. This first one was for test point 1. This one is test point 2. This one's actually test point 3, but it's referenced to the internal DAC5 of the device, which is also set to 512, and also DAC6, which is actually our test point 4 in our system. So that just gives you a bit of an idea that during initialization, these are set to 0. And these, let's see, there's also, yep, that's fine. So let's come out of that and go back to our main software. The ADC is actually giving us information about our voltage levels coming into the compass control unit, which is our plus or minus 12 volts primarily. And we've got the initialization of a 16-bit PWM. So it's a very high resolution PWM that we're using here. And that's been set up to produce a period of 20 milliseconds and a nominal 7.5% ratio for the PWM, giving us our 1500 microseconds or 1.5 millisecond signal pulse output, which is used to control the continuous servo. And then we have the initialization of the I2C, which is actually what extracts our data from the MEMS device of the CMPS12, which is sitting on the end of our compass pointer. We also initialize a trigger out. Now the trigger is used for several different things. One, it's used for the calibration frequency, which we mentioned here. This is that comes out of the trigger output. Sorry, not that one. Let me Yep, it's not that one at all. Let me just see if I can find the correct image for this. 2540 images, and there we go. Oh, that's the wrong file. I need to open it with a different software. Close that. Open with Paint. There we go. So this is what we would see coming out of that trigger input, which, and you'll notice here, let me zoom in again, view, whoops, wrong way, there we go. And you'll see this is the square wave that comes out. And what I'm doing is I'm going to tune the internal oscillator in order to get 500 Hertz, or as accurate as I possibly can here. So my scope is just showing me what the frequency is here. And I'm going to adjust this through the software in order to try and get this to read 500 Hertz, or as close as I can to 500 Hertz. So that's what we'd see on the trigger output. So let's go back to our software again. So initially we just set the trigger to 0, which is just a default level. And this now, when we start up the compass unit, you'll see a couple of instructions here. And this global PWM5 pulse width, PWM5 controls the actual continuous servo. And this is the absolute pulse width value that is given to the registers that control the servo. And so we have a global servo null point, and that is in general set to 1500, i.e. 1.5 milliseconds. And so the value in here is actually microseconds and is set to 1500 during initialization. But then what I do is I subtract 30 from that, and it gets the compass to move in a clockwise direction. And it's just to make sure the whole thing is working. So when you first power this up, you'll see the compass pointer moving firstly in one direction for 2 seconds, which is this bit here, and then it does the same thing again, but it moves it in the opposite direction by adding plus 30 to the pulse width. So rather than 1500, this would actually now be 1530. And it does the same thing again, and then it returns it back to its null point. Now in reality, what we'll see here is that all of the units I've ever played with here, that when it gets to this point here where we just actually have the pulse time, which is 1500, and we put it back to the servo null point, which is 1500, you'll find that the servo just gradually, very, very slowly rotates in one direction. And that's because the null point hasn't been set up properly, and that's something we're actually going to do with our options menu, which I don't know if I've still got it on here. There we go. Adjust servo null point. We're going to use option 2 to adjust it so that we can actually get the pointer to stop moving. So, so that's just resetting this. And here is a software that is actually now looking at our options, saying, well, which option have you selected, so that we can actually perform whatever function it is that we require. So if we select option 1, it'll be to calibrate the oscillator. If it's option 2, we're going to adjust the null point. 3, test attack. 4, to move the compass north, move the compass south, and rotate the compass clockwise, etc. And then we've got our main algorithms here, which we'll go into detail later on. So this is just a display systems option list. This actually displays all the options we saw on here. So this is displaying this particular bit here. Let's go back to the software. And let's see the system status. This is where we actually see, let's go back here. There's our system status, which is in this area in here. So we're looking at what's the state of the oscillator calibration and the voltages, etc. And let's go back. So that's what that's doing. And this is any display string error messages that we get. So that's just for that. So let's look at the calibrate oscillator. So what we're doing here is we're actually going to, remember I showed you, let me just get the image of this, yes. So here we're going to generate a square wave, and let's go back to the software. So it's already generating the square wave, And what I'm going to do is, by using the characters plus or minus from the keyboard, I can actually change the OS-tune register in the actual microcontroller to actually change the actual frequency. And so by doing this cyclically, I can keep on adding plus, 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 and it will gradually increase the timing of the oscillator. And equally, if I go negative, it'll make it slower. And I keep on doing this until I'm happy that I get this waveform with a frequency as close to 500 Hertz as possible. So having done all that, I can then press X to exit, and it will come out of this code. And all of this will make much more sense when we actually do it, but it's good to see the background software behind all of this. And when I finished it, I reset the trigger back to the out, and I changed this calibration status to 1, and that means that when I display this information, this line will say oscillator calibrated rather than oscillator not calibrated. So let's go back into the software here. So let's look at the adjusting of the null point of the servo. Once again, we're going to use the plus and minus signs from the keyboard to actually either increase the pulse width time or decrease the pulse width time going from the PWM. So by increasing it, we add 1 to the pulse time, and that will actually increase the actual pulse width. And so what we'll do is either see the servo arm, the pointer, the compass pointer, will actually start to either increase or slow down depending on how it's connected. So if we increase it, then we can increase the PWM time, and if we go negative, it'll decrease the PWM time. And when we've actually happy that we've actually got the servo to stay still in an initialized state, then this will be our set point for the rest of the experiment. And when we finish this, we can go X to exit, and so it just leaves this routine, and we can go back to another option. And once it's actually got this new value of the global PWM pulse time, it now saves it as the servo null point. And so now every piece of action that takes place is relative to the number that is now in the servo null point. So display the compass position. What you'll notice here, this is going off to get the compass data. So getting compass data is actually activating the I2C interface and extracting the data from the CMPS12 MEMS device. And in order to double check there's not a failure of the I2C, I come back with status messages that come back here from status. And depending on the numbers that come back, I can actually display these letters, and it tells me whether or not the I2C has failed. As I said to you, that if you don't power it up correctly, then sometimes the I2C interface fails, and this allows me to see if that has happened. So it's just a bit of test software that actually gives me information to know whether or not I've done something wrong. So that gets our compass position, and we turn that value from the compass value into a float value, and we display it on the screen, and that's what we will get here in our present compass position here. It's at 42.7 in this particular example. Let's just go back into software again, and that's the software that goes to extract the I2C information. So let's look at the test DAC. Now, we did discuss this, so the test DAC here, there we go. This is the waveform we're going to try and create. So let's just see how that is done. And so there's our test DAC. We're setting up a counter here in milliseconds. So this is a delay that we're going to put in here. And here we start off with remember the DAC has been set to 512 to begin with. So we take the DAC value depending on the direction. We're either deciding whether we're going in a positive direction or a negative direction. So in here, the direction is going up. So we take the DAC value, and if the DAC value hasn't exceeded its maximum value of 1023, we change the direction, and we also increment the DAC. Otherwise, if it's going down, we actually decrement the DAC. And then what we do is we take the value that we've just adapted, whether we've added to it or subtracted to it, and we load it into all of the DACs, the 1, 2, 5 and 6, which is your test points 1, 2, 3 and 4. And then we actually latch them all at the same time within these confines of the speed of the software, and this loads these values into the actual DAC and it produces a result. So it keeps on going around here, which will then produce this waveform going up and down as it executes that software. And when we press X, we can leave it, and so when we leave that software, you'll notice we reset the DACs back to 512 and load that value to ensure that they always revert back to 0 volts. So let's look at moving the compass to a north position. So what we're going to do here is we display the present compass position, and we go off and get the compass data, and we just double check to see if the I2C has failed or not. And what we're now going to do is saying, well, if the compass value is not close to 0, i.e. north, then we're double checking, because they're going to describe this in a little bit more detail. Let's assume the compass isn't close to north at the moment, it's quite far away. Then it means we can actually, which is the case here, then what we're going to do is make the speed of the pointer, i.e. the rotational speed of the actual servo, quite high. So we're going to add a 40 offset on this. So we're going to make it move quite quickly until it gets to 20 degrees within the 0 point. So that could be plus or minus depending on what's going on. Notice the angular difference between coming into the north position from either the east or the west position. So as soon as the compass then gets close and it's within 20 degrees of the position it should be in, which is ultimately north, it then decides to actually slow the compass pointer down. And there's a reason for doing that, because if you do this too fast and you kept this like this all the time and you actually had the pointer running at high speed, what would happen is the pointer overshoots and it ultimately can never get to this position because it oscillates backwards and forwards, which is no good. So the software tries to correct for that. So we can actually get the compass to go into our north position. And once we've finished all that and we've got back to a north position, we stop the servo motion by putting it back, the PWM of the servo back to its servo null point, that's why the servo null point is so important, to actually make sure the pointer doesn't move, because otherwise it will start rotating again, which is no good. So we always revert it back to its servo null point. Similarly, and to get to the south position, we're trying to get approximately to 179.9 degrees in that sort of like window. And it works in exactly the same way, extracting the data, and similarly applies the same algorithm so that it works very fast if it's within 20 degrees of south, i.e. 160, and that's plus or minus 160 if you look at these two bits of software. And so it just controls the speed at which the pointer gets to its final position. So it moves really quickly if it's far away, but then really slowly when it actually gets very, very close. And it stops oscillation and it allows it to catch where it has to go. So the last two things we're looking at is rotate the compass clockwise and rotate it anti-clockwise. So when we're doing this, what we're going to do is enter a value. And remember I said that the PWM for continuous servos has a general nominal point of 1500 microseconds, 1.5 milliseconds, and it's got a variation of plus or minus 500 microseconds. So what we can do is actually load a value. So we're going to get a value that we're going to change the speed of which this servo will rotate at. So I request a speed value, which can be 3 digits long, and it's a number between 1 and 500. If you load a 0, then it actually assumes you're actually exiting and therefore it just ends the software. Whereas if you load a value which is between 1 and 500, then it will load that value and apply it to the offset. So it takes a servo null point and actually then either, and note this is going in a clockwise direction, therefore we have to go negative to go clockwise. So either the pulse width is smaller, so we're actually making the pulse width smaller in this case, and that makes it go clockwise. And so the larger this value, the faster the servo will move. And similarly, when we go to the anti-clockwise direction, you'll notice that the value we've entered, which is the same function effectively, but what we're going to do is add the value instead, and that makes it going in an anti-clockwise direction. That just goes to show why you shouldn't copy and paste, because that should actually say anti-clockwise in here. And so all we're doing is getting the compass position so that we can actually just display that if we need to. And then finally, when we exit this, when we enter 0 into our value, when we go to get string here, if you enter 0, it will exit this software and will actually then reset the pulse width to the global servo null point. So all of the rest of the software is associated with the actual algorithms, but just briefly, these k values and k values, these are the constant values that are used in determining your algorithm. And if you've looked at the lab notes on this, you will know that you have to define the k value and the integration control constant as well, and this allows you to edit those and enter those into the software so that we can actually run those algorithms. And here we have the integration time, and so yep, that's it. And also we can actually apply gain and attenuation to our maths in our system, which we'll need to come into, because once the math saturates beyond the DAC values, we have to be able to change, either amplify the signal or attenuate the signal, so we can actually really see what's going on. But I've got to describe this in a later session. So that's pretty much the initial software for the compass control unit. Okay.